will share the screen. So yeah, ignore those, Rafid. That's total nonsense. Right. Okay, Namir, let me talk about that in a second. So there is something here that people were talking about that potentially, I should start the polls. That people have been talking about in terms of like actually is kind of a good thing, and how much of that is university, how much of that is Peel is a different story. Right. Okay. So one thing that people have been talking about is that people are desperate, I think, to return to in-person in one sense or another. Like whether or not you're an international student, whatever the case is, people I think want to interact with other people, right? It's good for your mental health, whatever the case might be. I say unless you're a mathematician and then interacting with other people you don't want to do, but whatever. Yeah, exactly, exactly. Not everyone actually wants to do that. But lots of people do, right? There are lots of people who desperately do need that. And one of the things that they say is that the universities, is that universities are actually in a really good place to be able to do this because one, our populations are in general, okay, obviously this is not universally true, but in general, our populations are young and healthy as a general rule, right? We have a lot of vaccination, right? Our vaccination status is phenomenal at the university. We've got very good like infrastructure for doing contact tracing and all these sorts of things. And so the argument, and you can say maybe this is a BS argument, I'm just repeating it. The argument is that the university is a place where people could return to in-person things and is in a good place to support that return, right? And that is why they're kind of, apparently there's a lot of pressure both from public health units and from the province to have universities return to in-person precisely because they're arguably one of the safest places that that could happen, right? Yeah, for sure. I mean, so I got a direct message saying, it's mentally exhausting with this kind of seesawing back and forth between going back and not going back. 100% totally, I agree. And, I have colleagues who are as worried about you as like commuting, right? I am, one of my colleagues lives in like High Park, which is a solid distance away, and doesn't have a car because he's always lived sort of downtown traditionally, and so he's trying to figure out how do I get to UTM now? So there's things going on with us too. Yeah, children returning to elementary schools before adults in universities. I mean, there's weird political stuff there, right? I mean, there's a real sense in which elementary and high schools are, obviously they are there for education, but they're obviously also there for, in some sense, babysitting, right? Parents do stuff during the day, and that's not to, crap on parents at all, but even amongst professors, we see, and we have very flexible schedules. When my colleagues started to have to take care of their kids, it just tanked their productivity, right? Because instead of, taking their kid to school and then having the day to like work, and then you go pick up the kid after school, the parents would have to like take shifts. And so we'd have to like schedule meetings around whose shift it was or whatever the cases would be. There were a lot of times when we were having meetings, like staff meetings at 9 p.m. on a Saturday, because, the kids were in bed and that was the only time everyone was free, right? So we were having like staff meetings at 9 p.m. on Saturdays and Sundays. Yeah, exactly. Yeah. Right. So stuff like that, because again, maybe it's your shift, right? Or like your partner's got something important that they have to do. And so you have to take care of the kid, but you've got to teach. So, whatever, you get them in on Zoom. So, it's rough for a lot of people. Some of us definitely have gotten through it a little bit better and have been in a situation to, not be as crapped on, but there's a lot of people out there for whom it's been really, really rough, right? Yeah, somebody pointed out Aziz isn't here today. I'll let you guess why not. Right, I don't want to I don't want to, his privacy, but yeah, he told me this morning he wasn't going to make it. So that's right. I was like, get out of here. Yes, Connie. Yeah, it is. Well, you can ask him next time to take you with him. When he comes back, you let him know. Is before or after your lecture? Usually it doesn't matter, Curdy. I mean, I think most classes, at least I know for math classes, I'm hesitant to speak for like history or something. Usually the tutorials are a week behind, so it doesn't matter where tutorials are relative to your lecture. Usually it's a safe bet, right? Because there are tutorials on like Fridays, and if you had to take them, or there are tutorials on Mondays. So, they kind of happen at both extremes. So you can't really expect people to plan them around their lecture around that. Well, okay, so Brandon, I mean, from my understanding of the people I know who have gotten COVID, they know it's COVID. Like, in the sense that it's even double vaxxed right now. So I definitely have a TA in another course who's for sure COVID positive, right? And we had to schedule around his tutorials and everything. And he's been in a really bad place. Like, he just feels absolutely terrible. He's only getting a couple hours of sleep every night. Like, at least, and it's hitting different people differently, obviously, right? But he's like, yeah, this is not a cold. Like, he got his butt kicked. High chance of going back online? I don't know. I honestly don't. I did predict that we would get pushed a little, but I don't know about, if we'll return to online. Booster shot? Not that I've heard of. I haven't heard anything about a mandatory booster shot. Ooh, Ahmed, that sounds nasty. Yeah, COVID in alone, that'd be rough. Yeah. Okay, so we're going to talk about a little bit of math too, right? So anyway, let's lock it up in about 30 seconds here. So get your votes in. I'm a little worried by the answers that I'm seeing, just a little. Oh man. Okay. All right, so here's where we are. That's pretty equally distributed, which again kind of signals to me that people probably don't know what the answer is, and it's just a lot of guessing. So let's talk about this. Let me just copy the function. I don't want to rewrite it all out. What a mess, right? Okay. So let's copy that. Boom. Here's our function. And we want to know the value of A such that this function is continuous, right, on its entire domain. So find a, come on, pen. I need to get a new pen. Okay, so find A. What? Such that, okay, don't die again, such that F is continuous, right? And so by continuous in this context, we mean continuous everywhere. Okay, yes, I will percussively maintain my bet. Okay, so the function is certainly continuous, right? It's continuous when x is less than or equal to negative a. It's continuous between negative a, and it's continuous when x is greater than or equal to a. So it's continuous on each of its parts. And really, the only tricky thing is we need to make sure that everything lines up. But one of the trickinesses that we're going to face here is that a appears not only here, but it also appears in the intervals themselves, right? This is kind of the trickiness that we're going to face here. And nonetheless, let's figure out what conditions on A we might need. So assuming that these joining points are the points that could give us some trouble, what we're going to do is we're going to say, well, let's examine the one-sided limits as we approach the joining points. So to be continuous at negative a, we need that this is true. Right? Does that make sense? right? Because this is the left endpoint where x is less than or equal to negative a, and then it's going to be 2x over a squared also at negative a. So we need these two joining points to meet up, right, in order for our function to be continuous. The left-hand side is pretty easy. The left-hand side is just -1. Now the right-hand side, again, we can actually just plug negative a into this. We're going to get -2 over a squared. So that's -2 over a. And look at that. Actually, we're already in a position where we could just solve this. So we're going to get negative a equals -2 or a equals 2. Okay. And so, and yeah, Rafid, actually, I have a Desmos thing. But if you, so yeah, what I would say is you probably wouldn't want to use Desmos as your justification in this answer, but if you want to use it to reconfirm, like that's a great thing. You can totally use Desmos to confirm your answer, and that would be okay. But it shouldn't be like your main argument, right? Of why you're like, oh, I plotted it and it seems like this value works. Okay, so we're lucky here and we managed to get a. We might want to just check the other side just to make sure, right? Because one option could be, I don't think it was in this case, right? But an option could be there's no value of a which works. Was that an option? No. But we just want to make sure that the answer is that there is a value. And so let's check the right side as well, the right join point. Just double check. So we're going to need that the limit as x approaches a of 2x over a squared has to be the limit as x approaches a of 1. Okay, now the right-hand side is still just 1, and the left-hand side is continuous. So we're going to get 2a over a squared, which is just 2 over a. I'm kind of assuming a is not 0 here. And yeah, we see a equals 2 does again work, right? Great. How do you know what's on the right and what's on the left? Right, okay, so how do I maybe put this? So when I did this first limit here, I was kind of looking at this thing, right? That this is where these two functions joined up, right? Because when you're -1 when you were less than or equal to negative a, and then you transitioned into this function 2x over a squared at negative a, right? And yeah, and then you would do the exact same thing for the other side, right? You'd be like, oh, this is the right-hand side. So those are the two different things that I used. And actually, okay, so the answer is a equals 2, which was D, but we coded a little Desmos thing here. Let me pull it up. Yeah, there we go. Okay, so we've got this. I'm going to pull up my other screen for a second. Cool. Okay, Emin, yeah, sorry, give me a second and I'll come back to that. Okay, sure, I'll come back. So what I've programmed here, though, is that this will actually plot the function for different values of a, right? So you can like mess around with this. And you can see this function isn't continuous here, right? It has like a jump discontinuity here and here. And if you go too far, right, still jump discontinuity, but there is a sweet point where they come together and voila, oh, look, there's the value of a is equal to 2, right? So that shows us that's actually, if you wanted to see what these graphs look like, that's actually how it fits together. And so we can see that we can actually draw this without lifting our pen from the paper, right? Yeah, exactly. Yeah, thanks, Brandon. Right, so the a's cancel out, right? You get 2a over a squared. And as long as a is not 0, you can cancel an a from the top and bottom. Okay. But here, Ahmed, actually, maybe let me see if I can use this to help. So here, this is the point. This is the x value here is negative a, right? We said a is about 1.6. So if we look at 1.6 here, it's about here. And so what we want to do is we want to compute the limit from the left, right, which will always just be -1. And then we're going to compute the limit from the right. And the limit from the right is changing depending on what a is, right? And we need to make sure that these two numbers match up and actually touch each other, which they do at 2. Is 2 like the root of the function? It depends what you mean. Like it's not a root. You can see here the only root is 0, right? Yeah, so everyone, we're taking the limit from the left, we're taking a limit from the right. We want to make sure that they touch each other, that they join up, And that's what we're doing in that process, right? So let me reshare my other screen. Right? So the dark green stuff here, right? That's us doing this work. And what we were doing is we were saying right here, we were saying, I'm going to take the limit from the left of the left function, then I'm going to take a limit from the right, and I want to make sure that those two things are equal and that they match up. And when we did that, we got an equation which we could solve for A, right? So by demanding that that was true, we were able to manipulate and figure out which value of A gave us what we wanted to. The second work beneath the blue line here wasn't necessary, but we could have done it as well. And it confirms for us that it works for the right join point as well, right? That's just basically what's going on. Okay, is everyone good there? Does that make sense? Hopefully that's okay. Oops. Okay, I'm going to assume yes. And let's do a different one. Oh, was I going to do this one? Sure, let's try this. This is a computational one. Let's see if we can get somewhere with this. I gotta reset the poll. There we go. And this is very similar to the sort of thing that we've done on tests in the past. Of course, there's no guarantee we do something like that this year, but definitely, yeah, something like this has shown up in tests in the past. Oh, really? Because I mean, it looks pretty ugly, but I mean, if you like it, that's great. It's okay. I mean, this is the last week of limits. Next week, we're going to do derivatives. Oh, but fun story. Yeah, for sure. I think definitely in general, people, you think they suck more, Brandon? You don't like derivatives? They're not that bad. They're not that bad. Doesn't derivative include limits? It does, but like you use limits just in the beginning in order to establish a couple of rules, but then once you have those rules, you kind of forget about them and you never come back. So we have to use limits a bit. I mean, that's why we're talking about limits, right? So you have to develop them a little bit in the beginning, but then you kind of forget about them and you don't use them anymore. Nah, partial derivatives are fine too. Are we doing antiderivatives? Yes, we will eventually. And like use of substitution, absolutely. I mean, I really wish, don't worry, it's not that bad, Curdy. You'll be okay. It's there's a lot of really fun math. I think that a lot of the way that math is taught nowadays has taken a lot of the fun out. Right? It's taken a lot of the fun out of math. And yeah, I mean, I don't even get to show you guys the really cool stuff. Like there's so much really fun, really awesome stuff with mathematics. But oh yeah, I think math is a ton of fun and it's really cool. Like there's so many really cool things that happen. It's kind of like, again, I always even kind of describe it. It's like astronomy, right? Like I hope that you all enjoy astronomy to a bit. Like when you think about all these cool things that can happen, right? Like who doesn't look at a picture of Saturn and is just like, man, that's awesome. You know, or thinking about black holes or things like that. Even if you just look at it from afar and don't get into the nitty gritties of astronomy, it's cool to look at pictures of stars, right? And math is very much the same way. Like there's lots of like really cool stuff that happens in mathematics. No, but here's the thing, math does too. Math has some like crazy cool things. And again, I can't show them to you because you know, we just don't really have time for it, but there's so much cool stuff. Yeah. I mean, and Ahmed, yeah, I mean, that's part of it, I think. And a lot of people are, I mean, everything is to some extent fun if you get it, right? And yeah, a lot of people, I mean, math has been built up as kind of this great obstacle for a lot of people in life. And so some people hate it, and that's okay. It's totally fine to not enjoy things. We can all enjoy different things. There's nothing wrong with that. But like legitimately, one of the things that's wrong is people use math to weed other people out. Like that's legitimately, like let's be clear here, people. You don't need the math that we're doing here if you want to go be an accountant, right? So if you guys want to do an accounting degree, like why are they making you do this? Well, the answer is it's because they're trying to weed you guys out. And I don't really like being used for that purpose, right? But that's like my job is to be a gatekeeper. I don't like it, but it is what it is. And then a lot of people end up hating math, and I don't like that. So it's kind of just a crappy situation to be in. Okay, well that's phenomenal. I love to hear that. Here, I'll tell you a cool math thing in a second once we finish this question. So I'm going to wrap this up. We're pretty low on participation so far, so everyone get your votes in. But I'm going to wrap it up in about 30 seconds here, and then I'll try and tell you a cool math thing. Okay, sure. I'm not offended if anyone hates math. It is what it is, right? Ali, yeah, 100%. Like I sympathize with that. I do. And it was the same sort of thing. Like I used to teach math 237 at St. George, and 237 was a course, it was the advanced multivariate calculus. And the thing is, they made all the actuarial scientists take that course, right? And the actuaries don't need to ever do any math that difficult. In fact, ironically, math majors didn't have to take that course, but the actuarial scientist students did, right? And that doesn't make any sense whatsoever. And when you ask the AXI department, the answer was there are too many people trying to become actuarial scientists, right? Because it got out that this was like a really good job. It paid well. You didn't have to take your homework with you, et cetera, et cetera, et cetera. So people flooded the actuarial science market. And then the AXI people said, well, we need to have fewer actuaries. So how do we do this? And the answer is make them take harder mathematics, right? So once again, even math-based things are using math as a gatekeeper, right? Assuming we are doing, so the answer is that, yeah. Why are we doing 4 minus 1 instead of f of 2? Yeah, okay, here, I'll take it up and then hopefully you'll see why. Hey, listen, I don't know what to tell you, man. Talk to the actuaries, right? It's the people who run the actuarial science program. It's those people, right? Those people have decided we're going to make them take math because math is hard, and we're going to try and limit who can enter our field by making them do something they don't need, but it's just hard for the sake of being hard, right? So, I mean, that happens. Again, I don't like I hope you guys all imagine, I don't want to be the bad guy, but they're like, hey, we need you to teach a math course. And they're like, yeah, no, go do it. So I don't like, being the person who keeps you from getting posts. Like, I don't want to do that, right? And yeah, Avi, that's absolutely true as well. How many people? Oh yeah, I assume you're okay. So let's do this. Let me repeat. Okay. Okay, I'm gonna have to make no, you know what? I'm not doing this. I'm gonna copy and paste the table because I do not want to write it all out again. So let's copy. Oh, you know what? While we're here, let's take the function as well. Right? Okay. So here's the table and here's the function. And I'm going to get rid of this like remnant word here. Okay, so this is what we want to figure out. Now, we're told that f is continuous, right? So we're told that f is continuous. So the idea here is that everything in this function is continuous, right? Gerber tab, I see it, but give me a second. Let me do this first. So everything here is continuous, right? So what do we got? We got a square root function. Yeah, that's continuous. We got x squared, that's continuous. We got f, that's continuous. And when you compose continuous functions, you get continuous functions, right? So we know, here, I'm going to switch to white. So we know that compositions of continuous functions are continuous. So that means that this whole function is continuous. And because the whole function is continuous, exactly, Curdy. What that means is we can just plug 2 into it. So what we'll get is that the limit as x approaches 2, f of 2 minus the square root f x squared minus 1 like this. So that's, we can just plug x equals 2 into this, 2 squared minus 1. Okay, so if we evaluate this, we're going to get the square root. So 2 squared minus 1, that's 3, right? F of 3, if we go up to our table, f of 3 is 9. So the square root of 9 is 3. So that becomes f of -1. And then if we check out what f of -1, that's equal to -4. And that answer was A. Right. Yeah, exactly. Yeah, this is composition and not the limit law. I mean, there's a limit law kind of like hidden in here, but right, exactly. How do I know it's continuous? Because the square root of x, yeah, exactly. All those things. So I mean, everything in there is continuous, right? Like the square root function is continuous, x squared is continuous, f is continuous. Like all the things are continuous. And when you compose continuous things, you get a continuous thing. So that's the idea, right? Like you could really break it down into a bunch of functions. But if you do that, it's just every single one of those functions is continuous, right? So does that make sense? Let me know if I need to go deeper into that. Okay, cool. I put the limit inside the bracket, but I mean, you can put the limit in the bracket if you want. So again, f is continuous, right? So I can push the limit inside. Right, because that was a lesson I gave you the other day. Right, so you can totally do that. Okay. This function in the square brackets is also continuous as well. So we're actually, now I could use a limit law and I could split the limit up if I really wanted to. Come on, pen, seriously. Okay, limit as x approaches 2 of 2 minus the limit. Right, so this is the limit law, right? There is secretly a limit law hanging out here. So if you wanted to do it like this, you totally could. Right, this limit here, the limit of the constant function is just itself. The square root is continuous, right? So you can put the limit inside of it if you want. So I think this is, this is probably more work, but like if you wanted to do this, you totally could. Again, you could say f is continuous, so you could push the limit inside. If you want to, you can just keep iteratively pushing this through if you wanted to, and that would be okay. Yeah, and Jose, if like you thought you did it wrong and you got it right, did you get it right for guessing or did you actually do it correctly? Because if you got it right, like if you got it right by accident, maybe, no, yeah, if you actually did it correctly, that's phenomenal, right? Like don't sell yourself short, right? Well, again, if you plug 2 into everything, though, it totally works out. It's the same thing. You don't have to do these steps, right? And you don't have to do these, like the other day when we did this step of like pushing the limit inside the function, it's because not everything was continuous when we did that, right? So we pushed in as far as we could until we hit a function that wasn't continuous. But if you know that everything is continuous, you can just plug the number in. So it ends up being like a really advantageous way of computing limits if you know that everything is continuous. And so in this problem, right, the only thing that was kind of abstract was the function f, and you were told that that was continuous. So that was nice, right? Because we could use that. So the root and f of x inside it cancel each other out, leaving 3. Ahmed, what do you mean by that? So the root and f of x cancel each other. Yeah, I'm not quite certain what you mean by that. Can you elaborate a little bit? So in a composite function, if the limit of the inner function doesn't exist, is there still a limit for the outer function? It is possible. In fact, those of you doing your writing assignments probably have seen this, that it is possible for the inner function to not exist, but the whole thing to exist. So like when it became f of 2 minus 3, and the f of x that was inside the brackets, and so when it became f of 2 here, let me scroll up. So when it became f of 2 minus 3, the f of x, maybe, okay, here, let me, so it's right here, right? This is the step. Yeah, maybe let me do another step in between. So f of 3, if we go to the table here, f of 3 is 9, right? So maybe let me write that in. So we get f of 2 minus the square root of 9, right? And then the square root of 9 is 3. Yeah, so there was just like, I skipped a little step there, but yeah, that's what happened. It wasn't the square root and the f canceled each other. It's that I evaluated it and it just happened to work out that way. So I can see actually, it does kind of look like they just canceled each other out, but it's because f of 3 was 9. Yeah. Okay, cool. I'm a little confused how it's not how you choose from. So yeah, Jacob, maybe let's talk about that in office hours or on Piazza, because yeah, that is a great question. But yeah, but that's probably better for office hours, which will be pretty quick here, right? In like 14 minutes or so. Okay, are there any other questions about this one? Everyone's good, hopefully. Okay. Okay, cool. All right, so let's see if we can't do another one here. Let's do this one. Okay, this one shouldn't take too long. You either know what they are or you don't. And then when you answer the question, see if you can say which is which, right? So what kind of discontinuity is A? What kind is B? What kind is C? What kind is D? That sort of thing, right? Like see if you can classify them. So I'm yes, except not for D, because it's asking at x equals 1, so be careful. Like that'd be right if it was x equals -1. Yeah, absolutely. Yeah, you're right. But in the case of D, it would be that it's just not, right? But yeah, absolutely. Exactly. Oh, and Gilbert, I actually missed your question. I totally forgot about it. I got distracted. And now I can't find it because it's buried in the chat. And it looks like, Owen, you might have also asked a question that I missed. Yes, Connie. So yeah, give or time. And I think, Owen, I might have missed one of your questions as well. If you two can just repeat what your questions were, I might be able to answer them. Though I think that they don't remember if they were necessarily, I don't think they were math questions. I think it was like post and stuff, but. Okay, I'm gonna do like 30 seconds on this question because I think most of you have it, which is pretty good. Oh yeah, I'm gonna copy copy these graphs too. Are you asking if theoretically it could appear, or are you asking me to put it on a test? Yeah, it could potentially be. Who knows? Something like that could definitely appear. This is totally the thing, like not necessarily so much in an online exam, but that's totally the thing, sort of thing I would have put in an in-person exam. Like 100% that would have appeared. Let's maybe make this a little bit bigger. Okay. So we were asked for removable. Yeah, Jen, yeah. This class will for sure remain entirely online. Yeah. Okay, so removable discontinuity. Does anyone remember what like the definition of removable is? And you don't have to write it out in like mathematics, just like describe it. Like, what is a removable discontinuity? A hole in the function, right? Right. Okay. So, but Curdy, so most of like B and C also aren't continuous at x equals 1, right? So removable discontinuity is a very particular type of discontinuity, right? And Brandon says it's when there's a hole in the function. And a very particular kind of hole, right? It has to be a hole like this. Okay, it's not B, right? It's not B, it's not C. It has to be that there's just like you went and you just put a little hole in it. A function that would be continuous if it didn't have a hole, right? Exactly. Oh yeah, okay. And same and Rafid, yeah, those are great ways of thinking about it. Like if you think about what the phrase removable discontinuity is that it says you could get rid of that discontinuity, right? So the idea that if you were to fill in the hole, it would actually take the discontinuity away is a great way of thinking about it. Come on, pen. Okay, I'm gonna go buy a new pen. This is insane. Davin, yeah, absolutely. When the left, okay, wait. So the limit from the left equals the limit from the right, but does not equal f of c. That's perfect, Emma. That is exactly the math definition. When the left-hand limit is not equal to the right-hand limit, but they both exist. Oh, Agam. So this is very close. What you just described is what happened in B, though, right? So the left and right in B, the left and right limits both exist, but they're not equal. Do you agree? All right, so the left, okay, my pen is just, I might actually be done and not able to write anymore. Nothing is bringing it back now. Exactly, yeah, that's a jump discontinuity. And Davin, exactly, though not necessarily undefined, right? So Davin, in A, the function is defined at 1, but it's just not equal to the value of the limit, right? So that's kind of the important difference. Yeah, I'm gonna try something. We'll see if I can save the pen, but yes. When you get the pen, don't forget about the glue. Thank you. Okay. So, yeah. All right. So that is what's going on with A. So B is what? What kind of discontinuity is B? Jump. Okay. What kind of discontinuity is C? Essential. Great. And D? Okay. So yeah, you're right. This is like a little unfair because you're right. It is a removable discontinuity, but it's removable at x equals -1. Exactly. And the question technically asked for what happens at 1, right? So in this case, we would say D is actually continuous at 1, but you're right. It does have a removable discontinuity at -1. Okay. Any questions? Hopefully the pen works. It's, well, because there are other types of, oh my goodness, look, it worked. There are other types of discontinuities that are not infinite. Okay, so for example, and again, this isn't the sort of thing that we would do in this class, but if we look at the function sine 1 over x, right? And of course, we wouldn't do this precisely because we don't do trigonometric functions. but try plugging this into Desmos. I'll do my best to graph it. It's pretty hard to graph, but it looks something like this, right? And so it's not that it becomes infinite at 0. This function has an essential discontinuity at 0 because it's not like neither limit from the left or the right exists, because this function oscillates infinitely quickly near 0. Okay, so that's what's happening. Does that make sense? Mm-hmm, mm-hmm. Okay, any other questions about that? We're good? All right, here, let's do a quick one because we don't have a lot of time, but there isn't really much more I want to do anyway. Okay, let's see. Do that one real quick. Let's relaunch. Oops, rested my hand on it. This is a fun one. We used to give this in 137, and we wouldn't give them the graph though. So it'd be an in-person exam, and we'd say, classify the discontinuity of e to the -1 over x. Right, and you had to figure out what its limiting behavior is. And it's one of these weird functions where it shoots off to infinity as x approaches 0 from the left, but it is 0 when x approaches 0 from the right, which is kind of surprising. Like, it would be easy to define a piecewise function that does that, but the fact that you can kind of organically find a function which behaves like this is, I think, a little bit surprising. It is. Yeah, it's some of you might have seen textbooks called early transcendental textbooks. And the reason why they're called early transcendentals is because functions like e to the x are introduced early. Whatever. You know what you meant. In my 157 class, right? Because I teach the hardcore first year analysis class, we have not talked about e to the x yet, or ln. Logarithms and exponential functions do not exist in that class. We'll talk about them in a couple of weeks, but it's a full year class, right? So we are already 14 weeks into class, and we still haven't talked about e to the x. That's not a function. There's no logarithms in Math 157 until week 9 or something, or sorry, week 9 of the winter semester. Yeah, probably not that late. Maybe week 5 of the winter semester. Limits can be infinity. We haven't talked about that. Yeah, if you want to come take 157 with me, Brandon, go crazy. Anyone who doesn't like logarithms, maybe 157 is the answer, right? 30 seconds and I'll close it. That's okay. You'll get a good taste of things with 137. Sweet. Yeah, that'll be good. If I pass this math and get accepted in the studies of management, is taking math? I don't think so. I mean, I'm not an expert in the management program, but I'm pretty sure there's no more math. There might be a second year econ that's basically stats, a stats class that you have to take, like econ 209, I think. But that's about it. Oh, okay. I know somebody, maybe it's only the economist, but somebody has to take Eco 209. And I think it's 209. I'm not even 100%. Well, great. So I'm your last stop, right? Okay, yeah. So yeah, Ali, give me a second. All right, yeah, it's the class is correct. This is an essential discontinuity. Our limit exists from the right. It does not exist from the left, right? So we've got this, let me get rid of this thing. We've got this limit approaching 0. Okay, so that one does exist. But as we approach 0 from the left, our limit does not exist. It's equal to infinity, but it does not exist, right? Equal to infinity is different. So it is a type, it's just a special type of does not exist. So this is an essential discontinuity precisely because one of the limits doesn't exist, right? Okay, see you, Brandon. So I think I had a direct message question, which is like, how do you choose math in first year math class? Man, if we had the answer to that question, I don't, the answer is we don't know, right? This is actually a major problem that we face in Math 157, is that we have a bunch of students who come into 157. So every year something phenomenal happens. This was actually a really weird year. But Math 157 usually starts out with like a full class of 60 plus 20 people on the wait list. So there are 80 people who want to take Math 157. 2 weeks into the course, the class only has 20 people in it. So 60 people drop the course in the first 2 weeks. And the reason for that is because there's a lot of people who come out of high school thinking that they're good at math, take 157, and then realize they just don't know enough of what they were supposed to, right? Yeah, and exactly, and there's so many math classes, right? There's 133, 132 and 4, 135 and 6, 137, 157. Like, how the hell are you supposed to know what to do? But the problem is that we often can't even describe to high school students what kind of math they should take, because we'll be like, oh, math 137 and 157 are exactly. High school math is it's not even just like plugging numbers in a formula. It's very formulaic. I call it like recipe math. Do you know what I mean? Like, sweet. No, I mean, that's phenomenal. And again, like, we're kind of teach it as we don't assume that you have seen any limits before. But yeah, it's math by the book. We're going to give you a recipe and we're going to ask you to like do the steps of the recipe, but you know, it's not really thinking too much beyond that. And like 137 and 157, I would love to show you guys some 157. I mean, I could show you 157, but I think I would just scare you. Oh, catastrophic doesn't mean anything, Wenshi. It's just like 100% us like playing a joke. Yeah, it doesn't mean anything. I mean, I can show you, but I think you'll just be like, yeah, that's not like, it won't mean anything to you. So, oops, shoot, I didn't want to close that. All right, here's what we did in 157 today. And this is what we're going to do we're going to do similar stuff to this in later. So I started here with this proposition at the beginning of the class. It says, suppose S1 and S2 are measurable. And then here are 5 properties of measurability, right? That weird M looking thing is the measure. It figures it. Basically, I'm just trying to say you've got subsets of the real numbers. How big are they? What are their size? So we spent today proving number 2. No, not proving number 2, proving number 5. So that if T is a linear map, then the measure of the image set of a measurable set is precisely scaled by the absolute value of A. It is English. And the proof of this fact, you remember how we do like complicated questions and you guys are like, oh man, that question took so long. That is the proof of that theorem. And that's just property number 5. But here's the thing, how much like, you know, when I harp on you guys and say like math is more than just like writing equations, like look at when I'm writing stuff, there's actually very little math here, right? I would say there's more words than there is math, right? Do you all agree? And part of that is because it's a proof, and proofs are very wordy and not tend to be mathematical. But like, yeah, hopefully you can see that you should, even though you guys don't understand it, you can probably read this and figure out what I'm trying to say, right? Versus it just being a series of equations. Actually, if you want some limit stuff, right, because we're talking about limits in our class right now, maybe let me try and find some limit stuff. Yeah, this is limit stuff. So you can see here at the top of the class, I have here is a piecewise function, right? Show that the limit as x approaches -1 is equal to 4. And here's the math for it. Yes, 157 is harder than 137. Would it be picky to give feedback? No, Abby, that's great feedback. That's 100% like great feedback. You should do that. Yes, I do have first years taking this course. Sure, we'll go back to 133 stuff. I mean, you should see the 257 stuff if you really want crazy stuff. Whoa, no, those are the videos. There we go. Well, okay, so, but no, here's the thing. So legitimately, I'm not even joking. There are some people who do better in 137 and 157 than in 133 or 135. And it's not necessarily the average student. I'm not claiming that any of you would go into 137 and enjoy it, but there are students who really suffer in 133 and 135. And then when they go to 137 and 157, they just crush it and they do great. And I legitimately have a TA right now who is TAing Math 157, right? He's a fourth year student. He's going to grad school next year. He's a TA for Math 157. Dude got like a 55 or something in Math 135, right? And then he came to and took 157 with me and he got like a 94. So it's totally possible these things do happen. And it's simply because, you know, so many of you hate math, but it's because you don't know what math is. And some of you, it will turn out actually are really gifted at math. It's just you're doing the wrong kind of math, right? Like this math maybe doesn't work for you. And once you see where real math is, you're like, oh man, no, totally, that's what I should have been doing. And it can convert you. And I'm certain that there are people in this class for whom that is true, right? That's true, that is true. But yeah, there's all sorts of like really fun, really cool stuff that happen in mathematics. Yeah, and some people do, right? Some people do find out that they're actually really good at math. It's just, again, what you guys learn in high school is not mathematics, right? Yeah, so here's an interesting question. So suppose I give you a checkerboard, right? You all know what a checkerboard is, right? Like it's 8 by 8 alternating sequences of black and white squares. And suppose that I cut out the two squares in a corner. Yeah, absolutely, Daniel. See you later. Okay, so like, here, let me ask you. Here's a question. All of you are actually have the math to do this. There's nothing crazy here. 4, 5, 6, 4, 5, 6, 7, 8. Okay, so suppose I gave you a checkerboard. Like this, right? This is my terrible checkerboard. So it's an 8 by 8 checkerboard. And I cut out this edge and I cut out this edge. Can you cover this with dominoes, right? Like 2 by 1 things in such a way that there's no gaps and no dominoes overlap. So I want any of you who are just interested in this, see if you can figure out this problem. Ahmed, which function do you want help with? The limit, here, let me write that down. So it's the limit as h approaches 0, 1 plus h to the 2/3 minus 1 over h, like this. No, is it, oh, it's minus 1 over h, like that. Okay, brackets, right? You gotta be safe with brackets. Because by order of operations, what I wrote down the first time was what you wrote down, right? So don't forget brackets. Okay, how would you do this? Oh, this is a beautiful question. Absolutely beautiful. The answer is, let me see if there's a good way of doing this. There's a cheating way, and the answer to it, so the way that you probably, when you saw it in the exam paper, the way that you wanted to do this, we have not learned yet. Yeah, so you could totally do that and then take a conjugate. You could, but remember, because this is a cubed root, we have to use our special conjugate, right? So remember, if you have the cubed root of x minus the cubed root of a, then the conjugate that you need to use is x to the 2/3 plus x to the 1/3, a to the 1/3 plus a to the 2/3. All right, the conjugate for cubes is actually really tricky. No, this is a really cool one. So again, when we talk about derivatives, have you seen derivatives before? Or is this like your first? Okay, so you have. So you know that f prime of c is the limit as h goes to 0 of f of, well, here, let's do f of h. Here, let me just do this. F prime 0, f of h minus f of 0 divided by h, right? So the derivative at 0 is this thing, if you go back and you remember the limit definition of the derivative. And so the trick here is to realize that if you define f of h to be 1 plus h to the 2/3, f of 0 is equal to 1. And so what that means is that the limit you gave me is the same thing as the derivative of 1 plus x to the 2/3 evaluated when x is equal to 0. And if we use the power rule to do that, we get 2/3 1 plus x to the negative 1/3 when x is equal to 0, and that's equal to 2/3. Does that kind of make sense? Like, if you've forgotten derivatives and that's not super clear to you, don't worry about it. Like, we'll talk about this stuff in a week or two, but that's how you would do it, which is to say, oh, this limit is actually really hard. The trick is to recognize it as a derivative, right? Could you have this sort of question in a test? Absolutely, you could. Yeah. That one method other than the conjugate, you showed it a few days ago. Sure, like that substitution. I could try and do this one with substitution. Geez, it's a little bit tricky. And the reason why it's tricky is because the h is inside the brackets in the numerator and it's outside the brackets in the denominator, but we might be able to do it. So let's see. Okay, actually, the first thing I would do is I would do this. So I'd say, so let's say I couldn't do this using a derivative. So what I would say is let u be equal to 1 plus h, so that h is equal to u minus 1. And then u goes to 1 as h goes to 0, right? So I'm going to now rewrite this limit. The limit as u goes to 1 of u to the 2/3 minus 1 divided by u minus 1. Okay, and the reason that I did that is I really hated the 1 plus h to a power. Do you know what I mean? Like, that just messes everything up. So by calling u equal to 1 plus h, now it just becomes that one variable to some power. And what did it cost me? Well, it cost me that instead of just having a single variable in the denominator, I now have u minus 1, but I'm okay. I'm really comfortable with that exchange, right? And now I'm going to make another substitution. So I'm going to let v be u to the 1/3. So v goes to 1 as u goes to 1. And now this limit becomes, so this becomes u squared minus 1 divided by u cubed minus 1, or sorry, v squared. And so that becomes the limit as v goes to 1 of v plus well, here, let me factor in case anyone is actually keeping up. V minus 1 v squared plus 2v plus 1. Cancel out the v minus 1s. Now it's continuous, so I plug it in. And again, this is continuous in V now, so I can just plug it in. I would get 1 plus 1 divided by 1 plus 2 plus 1. Y. Oh, no, sorry, this should just be V, not 2V. And we get the same answer. How come U goes to 1 and not 0? Right, okay, so look at, let me try and highlight this here. Look at this. So as H goes to 0, right? Think about what H, when H is 0, what is U in that blue circle? U is equal to 1, right? Does that make sense, Aim? Like, why U goes to 1 there? Sure. So again, remember, look at H going to 0 and look at this equation here on the left. When H is 0, U is equal to 1 plus 0. Right? And that's just 1. Yeah, exactly. Because when I want to change this limit here, right, as H goes to 0, if I want to replace all the H's with U's, I need to know what U is doing. So that's how, when you make that change, just make sure that you can do that as well. So if you wanted to do this without using a derivative, this is how you would do it. But you can see it's not obvious, right? Like this isn't necessarily easy. Like I had to use that trick twice in order to do this. And there is a way that we could have done it once, but you know, that's a little bit tricky. Okay, Curdy, let me read your message here. Let me see. Hold on, I need to pull up that particular writing assignment. And Christian, let me read what you're saying. Just give me a second. If it still was not continuous at V, would we need to repeat the last step again? So yeah, if you couldn't plug in V equals 1 and you still got something like 0 over 0, that would suggest that there was some more factorization you would need to do. And that, yeah. But if you got something like 2 over 0, that would be does not exist, right? So the only time when you really have to worry about that is when it is like 0 over 0. All right, which one was 3C? We did in class. Right, Curdy, no, yeah, the first thing you said is true. It's exactly 2, not approaching 2, it is 2. Hold on a minute, I got a direct message right before yours. And Curdy, let me know if what I said makes sense. Can you send me this week's tutorial questions? I don't know if I have them. I could dig through the course Slack and see if I could find them, but I usually let the TAs do their own thing. So if it's 2, I would find the point at F2. Yes, exactly. Yes, Curdy, that is exactly what you would do. No problem. Okay, let me download these. I can explain. Okay, I would let me, yeah, I'm getting kind of distracted here, so I'm going to write yours down. Example 5.13, y is multiplied by 1 over x squared. Okay, I'll come back to that. Yes, Curdy, yes, it is. I mean, I've looked over it very quickly, and so I might have missed something, but yes, I would say that it is. No, that's not what I want. Open the file. No, why? Okay, so 3E. Okie dokie. All right, here, I'm going to share a different screen here. Oops, I don't need you anymore. Yes. Okay. So 3E, right? So the limit as x approaches -4 of f of x. Okay. So as x is approaching -4, right? Here is -4. Hopefully, I hope you all can see my cursor. Right? Let me just check. Okay. So here is -4. And as x approaches -4, f of x is approaching -2, right? Because this is -2 here. But it's approaching -2 from above. So that's the inside function. So now that we know that the inside function is approaching -2, but it's approaching it from above, that's what we're going to plug in to the outer function. So now this is also the graph for f. So what is f as we approach -2 from above, right? From the right. Well, it doesn't make a difference here. It should just end up being 1. Exactly. So does that make sense? Yeah, no problem. So this example is not terribly interesting because we did approach -2 from above, but then the function was just kind of constant here. Maybe there's a more interesting one. That was me doing E in this example. Right, so we're approaching -2, and then the function as we approach -2 is just 1. C, okay, so C, so for C, the inner function is approaching what? What number is the inner function approaching as x approaches 0? Right, it's approaching 2, but we can say more than that, right? Because we usually need to think about, are we approaching 2 from above, from below, or from both sides? So is this function approaching 2 from above, from below, or from both sides? Okay, why do you think below? So are you saying that 4 plus x squared is generally less than 2? Because that's what it would mean to approach from below, right? Yeah. Right, so okay, but let's not worry about f of 2 just yet, right? We're still just looking at the inner function. So 4 plus x squared, I think we all agree is always greater than or equal to 4. Does everyone agree with that? Because x squared is always greater than or equal to 0, right? So 4 plus x squared is always greater than or equal to 4, right? So that means that the square root of 4 plus x squared is always greater than or equal to 2. And if you plot this, you should see that that's true, right? What were we doing? Square root of 4 plus x squared. So notice this function is always bigger than or equal to 2, right? So we're approaching 2, but we're approaching 2 from above. So I hate whatever stupid PDF thing this is. I need to get rid of it. So the inner function is approaching 2, but is approaching 2 from the right. So now we're going to say, okay, if I look at the function f and I approach 2 from the right, what am I doing? Oh, I'm following this curve right here. Right? And so that's equal to -3. All right, so you figure out what is the inside function doing, what number is it approaching? And then more specifically, is it approaching from above or from below? And then use that to evaluate what the outside function is doing. But the inside function isn't its own function. I mean, well, here's the problem. F is not continuous, right? Remember, in order to just plug it in, right, we need to know that F is continuous at where the inside function is 0. And this function is not continuous, right? F is not continuous at 2, so we can't just plug it in. Right? In order to evaluate the limit like that, we need to know that the composition is continuous, and we don't have that here. Mm-hmm. Okay, does that make sense? Is everyone okay with that? I mean, it's really just me pointing to the thing. I can try and do some math there, but that's effectively, the argument is just the written version of what I'm saying, right? So. Okay, so let's see. Can you be specific about which part is bugging you? So do you believe that, so you know that root 4 plus x squared is approaching 2, right? And do you agree that it's approaching 2 from the right? No, right. So remember, the right means that the value of, yeah, it's always bigger than 2, right? So if we approach a number, like see right here, when I say I'm approaching -1 from the right, what I'm saying is the number that I'm looking at is always bigger than -1, right? That's what right and above means. So if you look at the values of these functions here, hopefully these numbers show up. Notice that the y value is always bigger than 2. Like, you're not looking at left or right here. You're looking at the value of the function. The y value is always bigger than 2, right? Yeah, exactly. Because you're right, like x is approaching from both directions, but because, exactly, because we're going to plug this into the next function. And for that reason, we're really trying to look at what is the y value doing, right? Because it's the output, look at C, it's the output of this function, which is going to be the input to f, right? And the output of this function is the y value. So we want to keep track of what the y value is doing, okay? But on both sides, isn't the y value bigger than 2? Exactly, Jacob, exactly. So that means that I'm approaching 2 from the right, right? Or from above, because my values are always bigger than 2. So Jacob, that's exactly right. And that's why when we go back to this graph, now when we plug that into this function f, we're saying we're approaching 2, because think about the numbers 2 here. Okay, here, look at this. So on the left-hand side, maybe even let me make this graph a little bit bigger. Here's the number, the y value here is 2.543, right? That's the output of this function. If I go and plug that into this function here, 2.5 is about right here, right? And that's on this curve down here. Right, exactly. From the left is less than 2. Exactly. Yeah. So it'd be up to 1.9. What would be up to 1.99? Right, exactly. Yeah, if we were approaching from the left, then the curve, exactly, we'd have like a 1 point something around here, but we see there is never a 1 point something, right? We never dip beneath 2. Yeah, perfect. Could we just plug, Oh, wait, sorry, there's a direct message before you. I think you should draw that one line that shows what is left and right for up and down. Okay, sure. Let me see. Just give me a second here. Oh, no, that's the wrong one. Okay. So now we should be able to annotate without it destroying my computer. Annotate. All right. So this is, okay, I'm drawing with my mouse here because I'm not on my Surface. So this is above or to the right. Those are the same. Oh my goodness, this is so bad. So above, here, let me just put it in the chat. So I think, was it Jack who wrote this before? Above and right are the same thing, and below and left are the same thing. So when you're looking at the inner function, right, left is the same thing as below when you plug it into the outer function, and right is the same thing as above. Okay, and how do why can't I get rid of annotations? There it is. Okay, does everyone hopefully get that? Ah, damn it. What is going on? Yeah, this is why I hate Zoom. All right, maybe let me just stop sharing. Okay, there we go. Yeah, it's this thing, right? Like, oh, sorry, Wenchi, I must have missed your question. Oh yeah, sorry, I forgot about your question. So could we just plug x equals 0 into this directly? Yes, but that would only tell you that it was approaching to, not which direction it was approaching to from. Does that make sense? And for this question, it's critical that we knew that we were approaching from above. So yes, in your question, you're absolutely correct. You could just plug 0 in because it was continuous, right? That function is continuous at 0, but we needed to know which direction this approached from, right? So that was really important. For this question, we could have done this without a graph, I think, right? It does require a little bit of understanding of, algebra and how functions work, but you didn't actually, strictly speaking, need a graph in order to know that this approached 2 from the right. You would have had to make a little bit more of an argument to argue that root 4 plus x squared is always bigger than or equal to 2. But if you think about it for a bit, like x squared is always bigger than or equal to 0. So the number under the square root is always bigger than or equal to 4. Right? And if the number in the square root is always bigger than or equal to 4, then the square root's always bigger than or equal to the square root of 4. So we didn't need a graph here, but the graph certainly helps. Definitely doesn't hurt. It depends on what you mean by always. In this case, yes, we are always approaching from above, but obviously I could give you different functions where you wouldn't be approaching from above or the right. Like, for example, even if I just put a minus sign in here, that wouldn't be true anymore, right? Yes, stop complaining. Right, because now you'd be approaching -2 from below. Yeah, exactly. So for this one, yes, we would be approaching from above. For 3b, let me just double check that. Let me see what that says. 3b, so for a lot of these, you should, like in that case, in that question, we were able to approach 0 from both directions. I think as a general rule, and especially for the writing assignments, you should try not doing 0 from both directions simultaneously, but instead approach 0 from the right and approach 0 from the left separately and see what their behavior is. And I think that will make the analysis much, much nicer. Sure. For 3B, okay, let me see what I can do here. And 3B is a special one. So for example, that graph question does not have a question like 3B in it. What do you mean I can't minimize it? Of course I can. Stupid thing. Okay. I'm going to close these. Oh yeah, sorry. Yeah, that's true. Ahmed asked me a long time about example 513, and let me just get that out of the way, especially if he's got to run 513. That's true. I forgot about you. Thank you for reminding me. No, okay, so for 513, that's a limit as x goes to infinity. I wouldn't worry about that. We're not doing horizontal asymptotes in this class. Yeah, so yeah, you don't have to worry about it at all. It is. Yes, it is. I guess this isn't normally the pen that's in my mouth. All right, I would see you later. No problem. Yeah, I know. I definitely love this pen a lot. It is a beautiful pen. Okay, yeah, let me see what we can do here. Oh yeah, for sure. Right. And I have the converter because I would much rather fill in from ink than have, yeah, exactly. So I think this pen usually comes with the cartridges, but I got the converter because I would much rather be able to, you know, just draw ink from a well. I definitely think that's much more fun. Okay, so let me see if I can find another question. Where is it gonna be? All right, let me see if I can't get that on find Emmons download again. Where the hell is it? Huh. You know, f of 0, yeah, that's true. So Jacob, what I want you, okay, you tell me right now, okay, and you can tell me in, okay, sure, but you can tell me in the direct message, and that way we can do this. So I'm looking at 3B as well. Actually, you know what, let me just share. We can do this as a class, it's okay. Okay, so what I'm going to do, let's approach 0, but now let's not try and approach 0 from both directions. If I approach 0 from the right, what is f of x doing? Okay, it's approaching 2, as Connie says, but more specifically, it's approaching 2 from above. Jacob, do you agree? Okay, cool. So now let's plug that into the outer function. So what does the outer function do as I approach 2 from above? No, look at the function. Here's the function. What happens as I approach 2 from above? Right, the function is actually continuous, do you agree? Because there's no holes here. So as I approach 2 from above, I'm coming in along this path here. And what do I get? Jacob, do you agree? Right. But do you agree, or are you just taking your classmates for that? Like, you see why it's 6? Okay, cool. Now I want you, and class, don't say it, okay? I want you to do the same thing for the limit, okay? What is this thing doing? Okay, I only want Jacob to tell me. What is this thing doing? Perfect. And so now if you take that, so that's what, now we're going to plug that back in F. So if we do that for F, what do I get? So if I do what you just said, but with F, what do I get? Phenomenal. There you go. So what can you conclude? So from one side, you got one answer. From the other side, did you get the same answer? Yeah, there you go. But not, don't write that though, Jacob, right? That's not when you're on to write. Make sure you write the limit, right? But yes, otherwise you're right. Exactly. Right? You want limit of that is equal to 6. And Curdy, yes. So does that make sense? Okay. Okay, what? So we're not computing f of 0, right? That's not what we're computing. We're computing the limit of f of 0. No, we are, x is approaching 0, but we're not plugging 0 in, right? And that's why we don't just get f of 0. No, we're not plugging 2 or -2 in either. We're approaching 2 and we're approaching -2. That's the important difference about limits, right? We're not ever plugging anything into the function. We're just analyzing what the function is doing as we get close to those points. Yes, same. Yeah, exactly. Davin, yes, that's correct. Esther, yes. Yeah, that's also true. When she, with to some extent, like I don't want to, just give answers away. That's why I asked Jacob to only be the only one who answered me. I mean, there isn't a lot, Jacob, to write mathematically other than the argument that we just went through, right? So basically, what we just said in words is what you want to communicate in writing. That's why this is a writing assignment, right? Is you're trying to communicate, like it's hard to do some sort of algebraic manipulation to make that happen. So what you're going to say is, as x approaches 0 from the right, f of x does what? You don't care. That's not what you're trying to find the limit of. Right? What you're computing is this. The limit is x goes to 0 of f of x. So you don't want f of x. That's not what we're interested in, because that's actually not too hard to compute. Yes. Right? You're saying, I know that the inner limit approaches 2 from above and -2 from above. So now that I know that the inner function does that, I'm going to use that to evaluate the outer function. But yes, the feedback you give to your partner is generally counted as part of your grade. Yeah. Sure. I need to find one. Let me see. And see if I can't steal one from the book here, because I've made a bunch of these, but I don't want to just make one up. I guess I could just make one up. Let's see if I just make one up on the fly. Okay, let's see. So let's say I have a function. What do I want it to do? Let's say Okay, maybe this shoots off to infinity here or something. And then sure. So let's find the limit as x approaches to f of x. Okay, this one isn't too bad, but let's see how we do. How many percent is it worth? It's like it's worth 1 out of 3 marks or something. Is your feedback that you give to your partner? It's right. You're writing assignments out of 3, and it's basically worth 1. Okay, let's see if we can figure it out based off what I've drawn. What does so the inner function is just f of x. What is f of x doing based off of my drawing roughly as x approaches to? Let's do it from each side. Okay, let's not try and do it at the same time. So let's do the limit as x approaches 2 from the right of f of x. Okay, so what that means is I'm coming in like this. So what is, or maybe let's just do f of x right now. Okay, so what is the function doing? What number is it approaching? Right, okay, it's approaching 1. And it's approaching 1 from, yeah, this is just the inner function. And it's approaching 1 from above. Right? We all agree? Okay, so that means then when I compute the limit as x approaches 2 from the right of f of x, this thing, that's our inner function. So this becomes the limit as x now approaches 1 from the right, f of x, right? Or sorry, just f of x. And that looks something like, let's use a different color. So we're approaching 1 from the right, looks like this. Right, and we get, yeah, it seems like it's 2, roughly based off of my drawing. Does that make sense? Jacob, you good with that? Yeah, the red arrow is going to 2. Can it be the other way? In what sense? So do you want the other way as in like this, or do you want the other way as in like this? Like from the whole to the right. Oh, like this, right? So that would be if we were approaching 3, right? Because this number is 3 here, right? But this limit says we need to approach 1. And here's 1. Right? So we're approaching 1, but we're approaching 1 from the right-hand side. Yeah, exactly. Okay, and now let's do the other one. Okay, so that's just one side, right? That's the limit as x approaches 2 from the right. So let me get rid of these lines now. So we're going to approach the limit as x approaches 2 from the left of the inside function. Okay, so we're going to approach 2 from the left. So this time we're doing this. What is our limit doing? Okay, so this is no, but this one, this x is now to actually do this, right? Like I'm literally, this one is actually x is from the left. Here, maybe let me write this a little bit different way. So what I want to do here, and let me color code things, like really color code things. Hopefully this will make things better. So what I'm doing here, let's just redo the right, because let's not do a new one. I want to redo this, but like I said, let me color code, really make things clear. So what I'm going to do is I want the limit as x approaches 2 from the right of f of f of x, right? So this is what we're trying to compute. So what I'm going to do is I'm going to say set y to be equal to f of x. Okay. And I want to figure out, so now this limit here becomes the limit as x approaches 2 from the right, f of y. Like that. Right? Because y was equal to f of x. So what I want to do now is figure out, as x approaches 2, what is y doing? Right? So our question now, so as x approaches 2 from the right, what is y doing? Okay. And in our graph above, this is actually the x-axis, and this is the y-axis, right? So x is approaching 2 from the right, right? So the x-axis, x is approaching 2 from the right. And we say, well, what is y doing? Y is approaching 2 from the right. Right? So the answer sorry, 1 from the right. Does that make sense? Actually, let me put this in blue. Okay, yeah. But one is okay, right? So, okay. So now, just like you remember when we were doing the example earlier with like the U's and the H's and the V's, and I was asked, oh, why does U approach 1 when H approaches 0? And I said, well, listen, we want this limit to be in terms of y now, not in terms of x. So I have to change this, right? I can't take the limit of x when my function is written in terms of y. So I need to now rewrite my limit as the limit as y approaches 1 from the right, f of y. Okay. Yes. Yeah. I'm still recording. Everything of this will be up. Okay. So now I'm going to go back up to this picture, but I'm going to change the labels of the axes because look at what happened here. Okay. My input to my function is now the y-axis, right? So I'm going to now relabel this axis. This is now the y-axis, and maybe we'll say this is the z-axis or something like this. Okay. So now look at the graph. I'm taking the limit as y approaches 1 from the right. And I want to know what z is doing, right? And that output is that I get, what is this, 2? And technically it's 2 from below, but it's not, that's not a big deal. Right? Because now that we've got our answer, we actually don't care whether it's approaching 2 from the left or the right. So Jacob, does that make sense? In the sense that like, because we've got this function of a function, we got f of x, right? The output of one function kind of becomes the input of the other. So the axes kind of change. And hopefully the color coding helped us keep track of like, or maybe actually what I should have done is now x is doing that. And this from a color coding perspective is what's happening. Right. So yeah. And like, that's the same sort of thing that we're doing for every single one of these questions. It's just, we're trying to figure out what the inside function is doing. And then once we figured out what the inside function is doing, we can use that to evaluate what the outside function is doing. And we're just going to keep doing that over and over and over again. Right. So like you would write this out in words, like what I've written here, it is not very explanatory. So I'd say something like, you know, again, I don't want to kind of like write out a full thing here because I don't want you to just mimic my template. You got to find part of it yourself. But effectively, what I would say is something like, let's look at the inner function, right? As in the inner function, as x approaches 2, the inner function is approaching 1, but from the right. And if you want, you can define the inner function to be y. That would be totally okay. No one would be upset about that. Or you can just keep it as f of x, right? So as x approaches 2, the inner f of x is approaching 1 from the right. Therefore, when we compute this limit, when we want to compute this limit, it becomes this limit. And from the graph, we can see that the answer is 2, something like that, right? It's just instead of me saying those words, you would write those words down. There isn't a lot of algebraic manipulation you can do because you don't know what the function is. So it's a matter of just writing out and communicating your explanation when you actually do this. Exactly. And in this example, the answer is 2. Turns out if you do the limit from the other direction, it's also 2. Okay, so if you do the limit as x approaches 2 now from the left, f of x, so the inner function is doing this, right? So we're approaching 2 again from above. Let me maybe change the y here. And so now this time, I'm actually coming in, 1 from above. And so this time I'm coming in like this way, but it gives you the same answer, right? It's still equal to 2. With a limit of, what's that very last thing that you wrote there, Jacob? With a limit of y, is that y approaching 2? Yeah, exactly. Yeah. But approaching 2 from the from above. Yeah, exactly. Yeah, so you put the little plus in there, right? Or you can write it in words too. If you want to put the little plus, if you totally say it from above, it's okay. Yeah. And because both of your one-sided limits exist, so does the two-sided limit. So right, so the question asks you for the limit as x approaches 0, right? So that's a two-sided limit. Yeah, exactly, from both sides. And the way that you check if the two-sided limit exists is that you check, what happens in the limit as x approaches 0 from the right, and is that equal to the limit as x approaches 0 from the left? And if those are equal, then the limit from both sides, the two-sided limit is equal, or it exists. You can't approach what from the left? 0 from the left? You definitely can approach 0 from the left. Right? That's the whole -2 from above thing. Ariana, yes, but why? Now the question is, can you prove it? There is no solution, but can you prove to me there's no solution? Right? Because it's not just enough that you can't find one. You need to demonstrate mathematically that it can't be done. Ooh, nice. Yes, 100% that is the reason. Good job. Good job. Yeah, exactly. Yeah, every domino will always cover both colors, and one color is missing. Yeah, 100%. Good job. Is that Okay, so hold on. So like the graph looks something like this, right? So when you're approaching 0 from the right, you're coming along this path. When you're approaching 0 from the left, you're coming along this path, right? And like that doesn't have anything really to do with the fact that you're negative down here. So here's 0, right? 0 is just this big, is the y-axis, right? And so you're literally approaching the y-axis from the left. You're saying, you know, when I approach from the left, you're saying, forget all of this, right? You don't care about anything to the right of 0. So just look at what the function is doing to the left of 0. And the function to the left of 0 is precisely this thing, right? And so what is it doing? Oh, it's approaching -2. Yeah, but you don't care. You don't care that you start positive and finish negative. The only thing that matters is what happens nearby. Yeah, you only care about what happens at the very end. Yeah. Yeah, no problem. Connie, if both sides of the point we're approaching are above, it will be positive. If both are from below, it will be negative. Yes. And one each would be approaching from both directions. So if you're approaching from both directions, you actually just have to be, maybe Jacob, I'm not 100% certain. It'll depend again on compilation and if I end up doing anything else tonight. But Connie, it's 100% that the inner function could do something like this and approach from both directions. And then when you plug that now back into the outer function, you still have to consider what happens from both directions. Okay. And in fact, that's what happens when you think about, if you think about the limit as like x approaches 3, f of x, what is the function x doing as x approaches 3? Well, it's approaching 3, but from both directions, right? Like it's kind of a silly example, but if you plot the inner function here, what does it look like? Right? It just looks like, okay, my spaces are not very well drawn. Right? But as you approach 3, it's approaching, the inner function here is also approaching 3 from both directions, right? So maybe if we did something like, if we really wanted to spice it up a bit, maybe we do like f of x cubed, right? And if we drew f of x cubed, you know, near like 27, it would look something like, right? And in this case, I'm still approaching from both directions. So that's totally possible. Like that can happen. Okay. So Jacob, I'll tell you what, I'm going to try and do it. I usually, again, right after we do this lecture, I usually head out for a walk with the wife. So I'm going to get it ready to compile. Hopefully when I come back, it'll be ready. If I come back and it's ready, I'll try and get it up tonight. Okay, so it's not like 100% of a guarantee, but I'll make an effort for you. Okay. All right, everyone. Thank you for coming. Hopefully that made sense. No problem. Yeah, have a great weekend, everyone. And I will see you next week. Stay safe. Okay. Bye, everyone.